Yeah, Osmocom community TDM over IP. What is this all about? We will cover a couple of topics today. So why on earth? Then a little bit of background on TDM, time division multiplex networks. Some look at existing TDM over IP technology. The OCTOI, Osmocom Community TDM over IP protocol, the software, the current network status, and what kind of topics are still work in progress and what we have in mind as future plans. So, yeah, what is this all about? The point of all of this is to enable people to run legacy wide area network equipment. So that includes modems, phones, analog phones, ISDN phones, private branch exchanges, ISDN adapters, but also frame relay, X25, and all kinds of other older data communications equipment. Running that equipment at home is, of course, not very exciting if you cannot interconnect with anyone else. It must happen in a distributed fashion over the internet. I mean, it's only so much fun to connect two devices over loopback cable and without the rest of the network. And yeah, this basically allows us then to run old technologies from about the mid-1980s to about 2010 at a time today where the transport services for this equipment are no longer available from the public telcos, operators, carriers, you name it. So very brief background on telephony networks. This is really just the super high-level management summary. So originally, public switch telephone networks used to be analog lines with no digital parts whatsoever, which means we have baseband communication over twisted pair, well, rarely twisted pair, let's call it like that, on the last mile of the subscriber between the central office and the subscriber. And we also have baseband analog communication on twisted pair between exchanges in the nearby region. And for long distance calls, there was analog modulated carrier wave signals on coaxial cables, or then later on also microwave links of the long distance lines between exchanges across a country or even internationally. At some point, digital PCM, postcode modulation technology, was introduced primarily as a replacement for the analog carrier frequency systems between the central offices, between the telephone exchanges. The technology for this actually is much older. I think it's from the 1940s already, as far as I'm not mistaken. It's just that technically it was only feasible at a much later point after transistors, and with the beginning of integrated circuits, it became feasible to do that in a realistic way, and it's an economic way, of course. The initial technology used for interconnects using pulse code modulation between exchanges was called PDH, the plesiochronous digital hierarchy, and later on this was replaced by the synchronous digital hierarchy, SDH, which can transport the previous system. There's a separate OsmoDevCall on those topics. If you're interested in these, then feel free to have a look at that talk. There's a link in the slides, and the slides will be public. But also, if you search for that, you will find it, I'm quite sure. The external interfaces of those telephony networks, particularly the subscriber line, was still analog until at least the mid-1980s in many parts of the world, until basically the present day. But in some countries, and Germany was probably the largest market penetration from the mid-1980s onwards. ISDN, the Integrated Switch Digital Network, Integrated Services Digital Network, was introduced, and it introduced digital subscriber lines, meaning that not only the, let's say, the backbone between the telephone exchanges is digitized with postcode modulation TDM technology, but also the subscriber lines became digital. The two interfaces are the basic rate and the primary rate ISDN interfaces. They differ significantly in the capacity. Most, let's say, home users and small businesses had basic rate interfaces, and larger businesses then used primary rate interfaces, basically trunks of 30 concurrent telephone channels. In the present day, all of this is history. The telcos have mostly migrated to all IP telephony. You still find PDH, SDH networks even at public operators, but they are for maybe some very special legacy customers or for some internal legacy services. But I would expect in most parts of the world, it's no longer actively sold as a service to anyone. So it means if you want to play with this technology, you cannot get a subscriber line, whether primary rate or basic rate, to connect your equipment. If you can get it, then or if somebody sells you this service, then what you will get most likely is just some kind of adapter that basically terminates your ISDN on your premises and then does a voice over IP on the interface outbound from your facility. So there are these conversion products, but it doesn't mean that you really have ISDN service. Yeah, so the idea was to create a community network for those people who want to continue to operate or again operate or at all operate. Such equipment and play with not just ISDN, but any kind of TDM stuff. The distinction is basically that the TDM or PDH or whatever layer you want to call it is the transport, and ISDN is one possible system that you can operate on that transport, but there's many others. We will look at this in more detail later on. But basically, once you have a TDM line, then you can have ISDN or other services on top of that systems, and then on those systems you can have services. So yeah, how would such a network look like? Possibly what we want to build something like this. We have several people called hobbyist A to C. They each have some equipment like fax machines, phones, modems, ISDN terminal adapters, and some kind of private branch exchange to which they connect this equipment. And even before the OCTOI network, they could make calls between these equipment locally, and maybe they have a VoIP connection to the public network, and so on. But using particularly modems and ISDN terminal adapters over VoIP is not really possible in a reasonable way unless you have an extremely long list of special circumstances in which it works. So we interconnect those PBXs with some kind of access device over E1 line. The access device then provides TDM over IP connectivity over the public internet. So this device, this hub here at the bottom, runs somewhere on the internet, interconnects all the different access devices and the PBXs. So why do we need to develop something for this? Doesn't this all exist? I mean, we can just buy some TDM over IP equipment like such RAD devices that you can connect the E1 line and it outputs some IP traffic. Well, let's have a look at these existing TDM over IP technologies and where the constraints are. So there's two classes of TDM over IP. One is the so-called transparent TDM over IP, which is universal, meaning that it doesn't make assumptions of what system you run on top of it. It doesn't only work with ISDN, but it will also work with ABIS or frame relay or whatever else, ATM, whatever you want to put on this TDM interface. There's two major systems and, of course, some proprietary ones as well. One is called SATOP, Structure Agnostic TDM over IP. I put the RFC number here in case anyone wants to read up on it. The other one is CSOPSN, Circuit Emulation Service over Packet Switched Network. And basically, both of them transport raw E1 frames. That's basically a frame consists of 1 byte of every channel on E1 or of every time slot. On E1, you have 32 time slots, means basically 1 frame is 32 bytes. And these frames are transported over, depending on the vendor and the implementation, MPLS, Ethernet, UDP, you name it. What all of this technology shares is that it's primarily intended to use in a local area network or in a carrier backbone network, where you have sort of guaranteed quality of service and where you don't care about bandwidth. Because even if your E1 line TDM circuits are completely idle and not used, you will still have 2 megabit plus the overhead of the headers, so 2.5 or 3 megabits of traffic in both directions all the time, whether or not you use any of the content or any of the time slots on these interfaces. Also, since they are designed for local area network or carrier backbone networks, there's no support for traversing network address translation or for supporting dynamic IP addresses. So all not very useful for our use case in that context. The other option are the non-transparent TDM over IP technologies. What does this mean? It means that sort of the actual E1 or TDM connectivity is terminated in the converter itself. So it's not transmitting the raw TDM data like these 2 megabits I mentioned before over IP, but it terminates locally and translates it to some other more native IP protocol. And that means that such devices are then purpose-built for specific systems. And you cannot use them transparently just to have a bit transparent E1 interface between 2 locations. One of those is SIGTRAN IUA, the ISDN user adaptation, specified about 20 years ago, I think. There's very few devices on the market that implement this. It assumes that it's an ISDN line, so you cannot use it with anything else. It uses SCTP as a layer 4 protocol over IP, which is not very, unfortunately, there are many middle boxes, firewalls, whatnot out there that filter SCTP. So there might be some connectivity problems over the public internet. And also, it doesn't include any specification how the B channels, meaning the voice or data calls, are handled. It's a pure signaling solution for the D channel, the signaling channel of ISDN. So not very useful. Another such example that I've personally worked with is so-called Ericsson packet ABIS over IP devices. The proprietary protocol specifically for the use of Ericsson GSM equipment, which also uses E1 lines in the system. And yeah, it really doesn't make sense in ISDN context or in a frame relay context. So again, very purpose-built. So there was a case for a new TDM over IP protocol. The goals that were in mind are transparency. So it should work with any kind of technology that runs on top of E1. There is efficiency, so assuming that people participating in this network will be individuals with a normal end-user internet access, you probably don't want to waste more than 2 megabits in both directions all the time for nothing. Even if it's not metered, I think a lot of people would mind. Dynamic IP addresses are standard in such environments, so that is important. And there is, of course, the requirement of network address translation friendliness. So some people don't even have public IP addresses anymore, but carrier-grade NAT. And no matter how many levels of network address translation there are, it should pass through all of them. There's IPv6 support as another requirement. Of course, it should just work over v6 or v4. If we want to run this in the time to come, v4 will become retro networking at some point as well. And there should be some kind of authentication. So all of the above, aside from the authentication, are implemented already. The authentication is prepared in the protocol, but not in the current software. So how do we solve the bandwidth problem? Well, we do something called time slot suppression, meaning that the transmitter has a history of the last TDM frame. So we have these 32-byte frames, and the previous one we keep in memory. And before we transmit a frame, we compare the current frame that we want to transmit with the previous frame, basically do a diff between them, and we only transmit those time slots where the value has changed between those two frames. And that way we can suppress a lot of the idle slots which are not currently used without knowing the protocol or knowing what the structure of the information inside those time slots. So we don't sniff the signaling and assume it's ISDN and then use this information to determine which time slots are active, but we just do this diff, and that's the only source for our decision. There's also batching, meaning you can batch currently 32, but without fragmentation, you can do up to 40 E1 frames per UDP packet. So E1 has 8,000 frames per second. If we divide that, we result in about 250 packets per second. And since the minimum payload of the headers with sequence number and so on is 9 bytes plus UDP plus IP headers, if you add that up, you end up at about 70 kilobits per second on an idle E1 link, which I think is much more reasonable in terms of background traffic bandwidth consumption. And as soon as you start using time slots, of course, the amount of bitrate will increase depending on how many of those slots you start using, but it's completely dynamic. Yeah. The net friendliness, well, the easy way was to go for a classic client-server approach, at least in the initial incarnation. So this means the server requires a fixed, well-known IP address, and we don't use STUN or ICE or any of the modern technologies to establish end-to-end streams between in situations where both users have dynamic IP addresses. So here we assume the server is static public IP address, and the clients can then connect with dynamic IPs, which makes the situation much simpler. All of the messages, meaning the control plane, which is basically the user registration and traffic like that, and the TDM user plane, meaning the actual TDM data, are in one UDP flow to ensure that we don't have problems with multiple flows getting treated differently by network address translation in some way. The two implementations or the two scenarios that you can use right now is I'm going to describe those. The first one is where you have basically a physical E1 line on both sides. So we assume we have side L and R for left and right, whatever you want to call it. So these are physically disjunct locations or sites. At each of those sites, we have some kind of PBX, or it could also be a Cisco router with frame relay or any other device that has an E1 interface. We have an ICE1 USB, which is an open source hardware device for interfacing this E1 physical interface, connected over USB to some gateway, which is some embedded Linux device, which runs the Osmo E1 daemon software, Osmo E1D, which then speaks this new TDM over IP protocol over the internet to another site. And then we have a transparent E1 between those two sites. One of the two gateways will be running in server mode, the other one in client mode. And this was the first implementation that I did, and it's also the one which is used by the first 4 people connected to the network today. So basically, the user remotely has a setup like this, and I have the same setup here, which of course doesn't really scale a lot, since it means for every device, for every user, I need an ICE1 USB hardware device and a physical E1 line and a physical E1 port on my simulated central office here. So the second implementation was the so-called DADI trunk dev implementation. So in this case, the one side of the link remains the same like it is, or like it was in the previous example, but the other side is a completely virtual implementation without a physical E1 line, but with a virtual DADI interface. So DADI is a driver interface originally developed by the Asterisk community for attaching telephony cards to Linux systems for Asterisk. And the so-called DADI trunk dev is a virtual device driver for DADI. So all the applications, meaning Yate or FreeSwitch or Asterisk or you name it, they just use this like a normal physical E1 interface. But in reality, this is then implemented over the OCTOI TDMoIP protocol over the internet, and the physical E1 only materializes on this remote side. So basically, we can have a DADI device here in one location, and the physical E1 connectivity associated with that is remotely somewhere else. So that is rather useful in this context, because it allows the system, of course, to scale much higher. So the next 4 users, so currently we have, I think, 8 users connected to the system. They are connected this way, and that is going to be the standard way, of course, for all of the connections in the future, since it scales out rather nicely. There was a question already some time ago that LOIP is not mentioned, even though every Linux user already has it. So it's a MISDN system implemented by Jolly, who is also here in the chat and on the call, as we can see. It's another type of TDM over IP, but it's very specifically to ISDN. Also, I think it requires static IP addresses, so it doesn't fulfill some of the criteria. So it's not a match for what we have in mind here. And also, I think in terms of bandwidth consumption, it's not as far as I know, it's not as efficient as what we have come up with here now in this context. Also, LOIP means that L1 over IP means you have 2 virtual devices on both ends, but we want a physical device on one end, transparently exposed to another physical device or to a virtual device on the other side. Virtual to virtual is not very exciting. If you have some piece of retro computing hardware that you want to attach to something, then you need the physical interface in a transparent way. So how does the current hub look like for this network? It's still running here in my basement in Berlin, in Germany. That is supposed to change in a not too distant point in the future. But it's here in my basement. It's a Debian 11 system with this DADI trunk dev driver, which is a patched version of DADI, Osmo E1 daemon, and Yate. Now we have a couple of users attached to a physical TE820. That's an 8-port E1 card. So we have 4 ICE1 USB attached to that for 4 other users that are remotely attached over this original implementation with physical E1 on both sides. Then another E1 port goes to my local PBX. Another port goes into a Livingston Portmaster, a remote access server. Cover that shortly. And also another port now to a Cisco AS5400, which is a very high capacity remote access server that still has not been configured yet. There was a physical machine for this. I actually specifically bought a physical, like a main board that has PCI and PCIe slots and still has a rather decent CPU, so I can add all my legacy primary rate and basic rate interface cards to it. That machine died. So I migrated the entire setup into a KVM, and now we only have a single 8-port E1 card in it. And all of the hardware, the host controller, PCI devices, the DADI card, this TA20 card, and even the network interface card is all mapped into the VM by SRVIO. And that works surprisingly well, at least on this hardware. So who is currently connected? A number of people we see here in the list of participants. I think I may have forgotten even one user, at least now that I look at the list. My apologies for that. I should have checked the config files, but yeah, so roughly this is the list of participants these days. And some with the physical E1 on my side and some with the DADI trunk dev. The trunk dev has shown rather stable, but I still like to have these two different setups so we can compare and see if there's still some bugs or some performance difference or something like that. But sooner or later, everybody will move to the trunk dev on the hub side. What kind of services do we have now over this network? Well, there's the E1 transport layer, and on top of that, we have ISDN as a routing layer, you could say. The YATE installation on the hub simulates the central office switch side, and the remote and local users, local meaning my PBX, implement the user side. So to the PBX or whatever equipment you attach, it just looks like a public ISDN network that you connect to. The kind of services we have running and experimented with is audio telephony. That's the easiest, of course. Video telephony also works rather nicely. I've had a number of calls with ManaWorm using TView 100. That's a Deutsche Telekom branded device for an ISDN video phone that was sold some decades ago here. ISDN data calls, of course, from synchronous PPP over HDLC, over V120, X25, you name it. Analog modem calls, there are still some issues that we are investigating, but they tend to work rather nicely for most people, as far as I can understand these days. And the kind of problems we're looking at are not really, there's some problems with, I think, more with the TCP forwarding of the port master device that we're using right now. So yeah, how do modem calls look like? There's currently a Livingston Portmaster 3 remote access server. I'm just opening that link quickly. That's the wiki page. So this is how this device looks like. And yes, it's that worn down and rusty. So somebody really pulled that out of the trash and sold it on eBay. So this doesn't have all the modems yet installed. You can see the fan has been replaced to make it less noisy. Here's the E1 interface, and here we have Ethernet, really with all the classic interfaces. And I think it's actually a 10-base-2 10 megabit interface. So also retro networking on the Ethernet side. These are the modem cards that you slice in. There's only one in this device. I have another unit with fully loaded modem cards. Yeah, and this device basically is a remote access server to which can terminate up to 30 ISDN or analog modem calls. And after a lot of playing around, I managed to do what I wanted, which means that we can create services in radios now. That means we can specify a called party number. So I can just define an unused number in the dialing plan and make the portmaster provide a different service on each of those dialed numbers. So I think we have about 20 or so services by now, which is mostly telnet forwarding to BBSs on the internet. So you can actually dial from a modem or from an ISDN card into this, you dial some number, and based on the number you're calling, the portmaster forwards the modem data over TCP to a remote BBS somewhere on the internet. So you can dial into BBSs that are IP connected, but using the old legacy modem and ISDN calls. I can show that very quickly after the presentation in case somebody's interested. On my to-do list is to configure a Cisco AS5400, which I think with the modem cards I have has about 400 concurrent calls capacity or so. So that should definitely give us enough availability for the foreseeable future and probably for until the end of time. Some of the challenges in this entire setup. One thing I ignored so far is the topic of clocking. That's also the reason why we had to use this ICE1 USB device, and we couldn't just use any random old E1 interface card that you plug into a PCI or PCIe slot. We need a stable clock all over the network. And as long as the network itself was a TDM network, the clock came together with it, arrived at your doorstep together with the data. But now that we try to emulate this over the internet, we must make sure that the clocks are ticking at the same rate on all sides of the network in order to ensure that no underruns or overruns are happening. Because if there are underruns or overruns, it means that we need to drop or insert frames into the stream. And that breaks because the cycle slips and it creates phase discontinuities, which means modem signals are most likely going to die at that point, since something happens that doesn't really happen in a regular way in traditional TDM networks. Particularly not for V90 or V92 connections, where it was impossible basically to have such a situation. So the ICE1 USB device, about which there are also separate OsmoDevCalls in case you're interested, has a built-in GPS receiver and a clock. I call it a GPS DO. In reality, it's not exactly a GPS DO, but something like it. But anyway, it is a oscillator that is controlled, and it is controlled by GPS in a way that the number of clock cycles expired over a larger amount of time is exactly identical on all sides of the network. And this, if it's configured the right way, it has proven to work well. There were also some experiments by Sylvain recently disconnecting the GPS receiver, and even in 24 hours, it was still stable enough that he didn't run into this cycle slip situation. One challenge that we're facing, or we were facing, is packet reordering. So it seems, and we suspect, that particularly DOCSIS modems or DOCSIS, that is cable internet, do some packet reordering due to the way how they distribute packets over multiple streams, over multiple channels. That, of course, means we need to deal with it. The initial implementation used a stupid FIFO, which dropped all out-of-order packets, which, of course, meant that reordering led to a lot of packet loss. And later we introduced something we call REFO, random in, first out, which supports reordering of packets in the receive direction within the jitter buffer without any losses. So the reordering that we see, which typically is like 1, 2, 3 packets that get reordered, is all covered in that. Of course, there's packet loss on the links. So that means public internet is, of course, lossy. We cannot use TCP since TCP retransmission over the latency is much longer than our entire buffers on all sides. So that doesn't really make sense either, at least in long distance links. And stalling and so on, TCP is not the right use case. So we have to do UDP. Yeah, I did some research, and interestingly, I couldn't really find any studies or research papers on packet loss behavior of consumer internet that are less than 10 years old. So this was something that people researched, 10, 15, 20 years ago, but today I couldn't find any publications in this area. So all we can do is our own tests and see what we get. At the moment, we just have to accept it exists. Lost packets, of course, mean then that the receiver side is substituting frames, meaning there will be bit errors, or, well, it's not just bit errors, but many bytes of errors in the respective streams when it happens. In voice, it's not so dramatic. In signaling, it's also not so dramatic because the D channel has a CRC and there's retransmission mechanisms, so any corrupted signaling message will just be retransmitted. But again, of course, in case of modem calls, that's likely going to cause a lot of errors on the modem line. But yeah, that's what also the error correction systems in modems have to recover with, and in the end, it reduces the data rate. There are some thoughts on how to do forward error correction in the UDP packets that we send. There are some people who've done some experiments with existing UDP-based FEC, which does, like in theory, doesn't really do the right things in the way, like specifically how we need it. But yeah, there is definitely some room for development in that area to have forward error correction in the protocol to deal better with lost packets at the expense of increased traffic usage, of course. So latency may be another challenge. I personally am not convinced it really is the cause of some of the problems we're seeing. There's one participant, Christoph Lauter, here also in the chat and on the call, who is in Anchorage in Alaska at an RTT of, I think, about 230 or 250 milliseconds from the hub. So for ISDN signaling timers in layer 2 and layer 3, there's luckily no problem since they work fine over this RTT. There's some suspicion that this may have negative impact on fax and probably modem transmissions, but as I said, I'm personally not yet convinced that this is the latency is the cause of this issue. So that needs to be investigated yet. Yeah, so what are the plans for the future? Well, first of all, I want to migrate that hub into a co-location, not because I don't have the space here, but because my consumer internet connection is, of course, not the most reliable place to put such a system. Also, it doesn't scale indefinitely. So the more users we connect, the more we're going to run into limitations of my internet connection here. Yeah, if it's in a data center, then that's fine. I didn't have to physically touch the system for some weeks now already. So that's a good sign. Also, we've had no kernel crashes or anything for a long time. So it's a good sign that it's stable enough to move to some location where one cannot reach easily by plugging in some cable or doing something of that sort. Another topic is basic rate interface to the network. Right now, the only way to have basic rate interfaces is to have a PBX locally that has basic rate ports for phones, ISDN adapters, and so on. And then a primary rate interface towards the ICE1 USB. And that's rather high-end PBXs, which not so many people have. Whereas I think a lot of people have, or it's easier for them to obtain and less expensive, the normal consumer equipment that uses basic rate interfaces. And if we have a device for directly attaching over basic rate interface, many more people would be able to participate in this network. Another thing on the to-do list is a frame relay switch at the hub side. So that's a second additional service that's completely independent of ISDN service that we have. So it would basically be a second instance of the DADI trunk dev with then the Linux frame relay code performing the network function and whatever Cisco other routers remotely attached over ICE1 USB to participate. We did a bit of testing, Sylvain and I, with this recently, and it worked out of the box just fine. So it's really just a matter of configuring it and maintaining it. But the underlying Osmo E1D, the protocol, everything deals fine with it. And then, yeah, of course, some exhibits at Hacker and Vintage Computing events. That's actually what I started even before this community TDM over IP at the last CCC Congress at the end of 2019. I had an installation, a similar installation, I mean, not with TDM over IP, but with a Livingston Portmaster as REST server and an Auerswald PBX and some modems and so on, to show people or to either to show them if they didn't witness these times, or to bring back memories of people to dial up BBS's internet access and so on. And now we can, of course, interconnect such exhibits at retro computing events and connect them with the hub and access services remotely as well, which maybe is even more exciting than just doing it locally. So for the ISDN basic rate interface, there is no support in the protocol yet. The stupid way to do it, of course, would be to say, well, okay, there is 3 time slots instead of 31, and we do everything else the same. Not very bandwidth efficient, but okay. We'll see where that ends up. In terms of hardware, we again need a S or T interface that has clocked from a GPS disciplined oscillator. In this device, I don't want to have a USB interface and another Linux box, but I want to have a fully integrated device, meaning that basically you have your S interface on the one hand side, your basic rate interface, you plug in your ISDN equipment. On the other side, you plug in Ethernet, and that's it. It connects over the internet to the hub, and you have your ISDN services. I think if we create this at some point, if we manage to complete that, it would enable a lot of people who don't have this kind of detailed system level IP networking, Linux, and so on background to participate. People who just collect phones and maybe who also collect digital phones or other digital communications equipment without the deep technical background. The status of this is that a first breakout board has been designed for the chip and the passive parts. I ordered the circuit boards today, so in the next weeks should be able to assemble some prototypes of that. This is just the chip for the ISDN side, and it's not fully integrated yet with the system on a chip I want to use for the Ethernet side. So that's really just a very first step to validate everything, to prototype it, and once we know it works, there will be a second board which then integrates all of the parts on one circuit board. Yeah, long-term future plans. I want to work on the free and open source software soft modem situation. There's 2 projects, Lin modem and Span DSP. They both implement some parts of some standards. Span DSP is very fax-centric. Lin modem is modem-centric. Span DSP doesn't have more than, I think, does it do more than 9,600 bps? I'm not sure, maybe 14.4 or 19.2, but certainly no 33.6 kbps or no V.90 speeds, whereas Lin modem has some of those more modern V34, V90 stuff. So yeah, I did a bit of experimentation, but it's very early at this stage, and that will likely be longer term in the future. We need to investigate what is the throughput limitation with the Portmaster 3 at the moment. That's also one reason to set up the Cisco AS 5400. So we have a second RAS server to see whether we are looking at bugs or problems that are specific to one vendor or one firmware, or if it's really a problem with our network. Yeah, X25 is also something I want to play with, specifically X31, which is doing X25 over the D channel of ISDN. And that was used a lot in payment terminal applications here in Germany. So all the card acceptance terminals at restaurants, fuel stations, and so on, they were all running over this service, or most of them, some time ago. Yeah, and with that brings us to the thanks slide. So thanks particularly to Sylvain for the ICE1 USB device that he developed, and all his help also in recent months in the context of the TDM over IP network. All of the early participants listed here. Sorry if I forgot somebody. My apologies. And there's a couple of links in the slides to the respective projects. If you want to follow up on that, if you're not aware of those yet. And now, before doing some demos or something like that, or having a look at data and statistics, maybe room for questions on the record, if anyone has some. Since we're sending a fixed number of frames per second over IP, would we feasible to derive a clock from that? Yes. I think it's realistic to have one of the two sides of the link without GPS, but really only in the context of this new basic rate device where the Ethernet is integrated with the ISDN side. So we can really get proper IP packet timing and average that over time, and use that to control to steer the oscillator for the ISDN side of the interface. With the E1 interfaces that we have, that is not impossible, but very difficult, or much more difficult, since we have so many different layers in between, in a sense that the IP packets are received by some Linux box, but that Linux box doesn't have low-level control over the oscillator, which is in a USB-attached peripheral device, which has the GPS receiver and so on. So I think you can make it work, but it's much more effort on that side compared to the basic rate side. I currently don't think it's a priority. We need to make sure that all of this is working, and like the GPS DO is an easy way to sort of solve the clock problem and to concentrate on other parts. And then if the other parts are all there, one can revisit and see what can be done in terms of clock slaving over the based on averaged of the packet timing on the UDP packets. Yeah, I don't think one needs to go to a hardware NIC timestamping in this use case. We don't need that level of accuracy, but yeah, there's a lot of work in that area, of course, but luckily we don't need to go there. One thing also to keep in mind is that all of this is developed in a way that it's not like it's not mandatory to attach to this hub that I'm building, right? You always have to think also of situations where two random people want to have, let's say, a private leased line between each other, and they can do that with all of the technology that's out there now. But in that case, there is no central hub. So again, they need to have somehow share a clock, and then at least one of the two has to have a GPS DO. That's not possible in another way. Yeah, and I agree with Christian. That's why I said that timestamping doesn't make much sense. And we are talking about much longer intervals where we integrate all the timing over a longer period of time, and then with the result, we steer the oscillator. For potential software, future software modem banks, the strategy of frame in, frame out to just mirror the clock of the other side might work, though. Well, yes and no, only if you look at one particular channel, right? But we are looking at entire trunks of channels, and there you cannot really take that approach because it's a TDM network and there's one clock, right? So it's it's quite a bit of a different situation. So I think for the TDM network, the way to go is that you make sure that you have a proper synchronized clock, and that you don't really run into situations where you slip clocks, and then you have exactly the kind of timing that used to be the case in TDM networks, and that's it. Yeah. Okay. Good. Then I can share some. I don't have an exact plan of what to show. I mean, of course, we can establish some modem connections or something. Not sure how exciting that is. I could also show you a bit about the hub in case somebody is interested. For example, how these services are configured in radios, or how it looks like to access the Livingston port master. So we'll just see where we go. No, that was not what I wanted. We could, for example, telnet into the port master, or no, let's start with the Devo. That's basically the central hub. So here we see output of the Yate monitor. So if I'm, for example, going to call from my telephone some number, let's say, then we get here, of course, the log output of Yate. This is now the port master trying to establish a modem connection. In the background, we see the ISDN frames here, like the setup message. Let me just terminate that call. So we get less audible disturbance here. So we see the dial number, who is calling on which trunk. Here, AUCM2 is the trunk number in Yate, and so on. It's a standard Yate installation. If you've seen that before, there's nothing really exciting about that. We also here, for example, have the log output of the Osmo E1 daemon. This one is the virtual one. No, this is the physical one. Sorry. We're looking at the journal and not as a specific one. So let's look at the Osmo E1 daemon, one of the two ones running here. This one is the one for the virtual trunk. So I can here list the, I cannot scroll back like that because I'm on screen. So we see we have one server running, and we have TNT FR. That's the frame relay testing I did with TNT here, the statistics. We have our Polish participant. We have here Dr. Leek. The connections that are established here. We can, of course, also look at the log. The log typically, that's, I don't, there we go. Now we see some log output. So basically, it only logs when there is some activity in the frames. So all the frames that don't contain any time slots are not shown. But here we see, for example, from several network participants, the time slot mask. This is time slot 16. So we're seeing signaling frames here on the D channel. Number of time slots is 1. So only one time slot was active in those messages. And if I were to call any of these gentlemen, now I would have to look at the phone book. Maybe some of you are remote. If anyone is ready to make a call, we could see that there's much more stuff scrolling through at that point because we have more channels active. There we see. We see now. We see the time slot, the highest time slot, so basically time slot 31 is being used, and we see lots of more log messages since this time slot is now active and the call has been established. So this is just the debug output, and we have lots of statistics and counters. I will get to that and show a couple of plots shortly. I just want to show some other parts of the system. So if we go to free radios, this is basically the way how the services are configured. So we see here the so-called call check service is being used by the port master. It's a special, normally Radius is used to authenticate users after they have logged in. Here, this is a special way how Radius is used. Basically, at the time the setup packet hits the port master. So if somebody dials this number, then Portmaster will issue a call check Radius query to the Radius server. And here at the Radius server, then you specify what should happen with the call in this case. So you can say, well, basically, it's a login service with our login to this destination IP address and port number. Or if we look at any of the other services, so these are all the forwards to different VVSs. Yeah, so we see, excuse me. Yeah, that's some connection now. We can actually use that. If you can keep your modem call running, please. We can just quickly have a look at how this looks like in the Portmaster. But yeah, just this I think is rather nice. So we can any number of different destinations and VVSs that you can dial into it can just be configured in the radius. So what we want to do, no 92.68.7.4. So now we are in the Portmaster, and we see there is a connection right now active at the speed of 31,200. It's using V42 BIS compression and so on. We can say show M0, and then we see the speeds for uplink and downlink that are currently negotiated and some other statistics. Here we see the serial port to which this modem is connected, and we see it's a login service. It uses, no, this is actually the wrong one, sorry. It's S1, I showed the wrong port, yeah. So here we see also the speed, 31,200, and it's connected over Telnet to this remote destination. We see caller IDs and so on and so on. So that's how it looks like on the hub side. Unfortunately, no decent low-level statistics about the modem. Even if you debug, if you enable the debugging for the modem, it doesn't really tell you much other than the speeds it negotiated. Not very useful for any kind of low-level debugging. Let's look at some link statistics. So what we are seeing here are graphs for the connection that we just saw, where the modem call was made. So this is the long-term view. Let's look at the last hour. What kind of graphs do we see here? We see on the upper graph here, we see the FIFO level in the E1 originated direction. We see there are always some drops, but normally it's at 32 frames. That is normal. The drops, at least some of them correlate with new connections. So we have, no, it's actually not new connections, time slots active. Well, okay, we always have to look at the scale. This is actually not surprising. We have 24 to 32, so that's a perfectly normal FIFO level. It dropped to the bottom doesn't mean it dropped to 0, so that's perfectly fine. Also here, the sawtooth pattern that we are seeing is that's the E1 terminated FIFO level. So basically, I have an E1 physical device with a clock slave to GPS, and I have IP packets coming in. And every IP packet contains 32 frames. So when an IP packet comes in, my FIFO level rises, and then the 32 frames they basically get transmitted over the E1 interface, and then again an IP packet comes in. So we see the FIFO level rise and fall here in cyclic patterns. That's all fine. About 200 is the nominal, 200, 220 is the nominal level of the number of frames that we have in that FIFO. In this graph here, we have two plots in the third from the top on the number of substituted frames is that pink line. So we see very rarely that some frames need to be substituted, which means that basically some packets were lost completely. We here have a packet out of order counter as well, where we see whenever there's packets out of order. And here finally at the bottom, for example, we see the number of time slots active. And here when the modem call was started a few minutes ago, we see, of course, the count goes to 2 time slots here in this example that are being used on this line. We can look at some other links in comparison, just so you can see a lot about the network here. So the link to Alaska, for example, to Christoph looks quite a bit different. So again, looking at the last hour, this is the time slots active. The pattern looks quite different, but that's just the way how it's used. So that doesn't really mean anything. Packets out of order, we had some very few peaks. And on the FIFO level, so the order of the graphs is different here, sorry. But the FIFO level, we see we are already reaching what 600 FIFO depths of 600. So we see a long-term change. So here we had a new connection. That's this spike here in the connect accepted. And at that point, the FIFO level dropped again to the initial 200 packets in the FIFO. And then over time, it rised higher, 300. There was a jump. That could be some BGP route change, possibly, that switched to a link with shorter latency, increasing the number of FIFO. But in general, there's a long-term trend of the FIFO growing higher and higher at my end, meaning that the remote end is transmitting at a faster frame rate than my local E1 clock. So that means that either the remote equipment is not properly synchronized, or GPS around the globe is not as stable as we would normally assume it is. But in general, so Christoph writes that he loses GPS from time to time. It doesn't matter really. The GPS, as the long-term stability is rather high. So we need to investigate what's happening there. But I still think somehow the remote equipment is not really following the GPS clock as it should. But we will figure that out at some point. It's just something to look at. It's not happening on any of the other links, so it must be something with the setup or with the GPS performance over. But in any case, it shouldn't drift. I mean, there could be a short-term difference in clocks from different GPS satellites, but high temperature changes. Then you would see, you would be able to correlate them when the temperature changed. So if you had a temperature change exactly at that time, then that. But temperature changes one sees in the plot of the GPS tuning, which I don't have here. Why don't I have it actually? A good question.
In the fourth line, it says GPDO tune fine in pink.
It does? Am I blind?
Just above your, there is the pink thing, and to the left of the pink thing.
Sorry. Okay, indeed, yes. So, the very, how can I say, noisy line here. We have the coarse tuning is basically stable. That's the pink line here at the top of this graph. The fine tuning line is the one here. So that basically shows us the tuning value that we put into the GPS. The tuning value that we use to steer the voltage controlled oscillator based on the GPS reception and counting the clock cycles. So you can see in my case, it's relatively stable. Even if we look at, yeah, there was something happening at some point here. You see there was some rising all the time, but then falling abruptly. That is also likely a temperature related phenomenon, that the temperature changed and therefore the tuning changed considerably. So you can easily see when I open the door, or even other things, if you look at those graphs. Yeah, as Christoph also said. Correct. Yeah, I don't want to bore you with more graphs. So if anyone wants to see something specifically, I'm happy to show it. Otherwise, that's it from my side.